halfway through the alphabet here. So one of the things to keep in mind in Cassandra is that as I add this node right here is going to own this entire range from A to N. The previous node, the node we already had in the system, would then own the range N through Z in the system. So as you add nodes to the system's relatively dynamic. New nodes take over ranges that other nodes previously owned. So as we bootstrap, if we were to bootstrap a new node into the system, we already had A and M. If we were to bootstrap this node G into the system, G would basically tell M, hey, I'm taking a piece of your range. And so M would partition his data setup into his own. He would keep whatever he had before and then transfer this A through G to this node over here. And then G, after he builds his indexes and everything he needs to own this piece of data over here, he would tell the other nodes in the system through gossip, principally the seed node, hey, I'm ready to take over this piece of the ring right here, and I'm going to join the ring. So adding nodes in Cassandra is relatively easy. It's a painless process. It's something that happens without much intervention. You just have to tell the node as he comes up where he's going to join in the ring. And he comes up and he manages the process of getting the data that he needs, building the indexes and everything else he needs to join the ring, and he just comes in. Cassandra is a key value store. So each of the keys are placed based on a consistent hashing function. So the partitioner itself, which is pluggable, by the way, so you can use a random partitioner or an order-preserving partitioner. Most people use the random partitioner, but that's what determines the location in the ring, such that if I have some key that maps to C in this ring right here, it would come, somewhere on this line right here. That one of those replicas would certainly be assigned to this node right here because he owns this range. In higher replication factors, however, each one of these nodes would be assigned two separate ranges. So G right here would be assigned this range. For a replication factor of 3, he would be assigned this range, and this range. And for the simple replication factor strategy, it's always the case. So if I have a piece of data that falls right here, the nodes that would own that piece of data would be G, M, and T. These are implementation details that you as a user wouldn't have to know, but if you were administering a system or using Cassandra on a regular basis, they're things that you would actually want to know. Well, at least you would never have to know, maybe you never want to know, but it's something you probably certainly investigate and find that it's a very simple and straightforward thing. So one of the questions that comes up is, I've got all these nodes out there, how do I access my data? And how do I do it in a way that gives me a very scalable access pattern? So each node can be a coordinator in the ring. It manages writing and read repair, and also the success depends on the per call consistency level request to the coordinator. So the coordinator is going to make sure that the reads and the writes conform to whatever the client asked for in terms of its consistency level. So here, if we were writing a particular piece of data with a key of C into this node A, A would coordinate at a replication, say this is a replication factor of 3, and then we require at least two writes to be successful. Then C would fall on this node line right here. We know that there's a replica here, here, and here, replication factor 3. So A can talk to G and M here to get a response and coordinate that response to the client. So again, in Cassandra, there are no single points of failure. Every node is symmetric. There's no difference from one node to another node about how it deals with the data. Multiple data centers work naturally with Cassandra, and you can set it up so that different nodes are assigned to different data centers, and it uses a system called snitching, where I can use a property file on each one of my nodes and tell it, these nodes in your system live in this data center, these nodes in your system live in another data center, so that it can make smart decisions about which replicas do I want to, if I'm doing a consistency level 1, for example, which replica do I want to ask for this data, because I want to ask for from the most local replica for the data that's out there. Also, it's very monitorable. Almost everything that we could expose as a JMX counter is exposed as a JMX counter. You can see your latency, you can see histograms, you can see all kinds of stuff about your data and your access pattern out there. There are lots of people out there who are actively creating Cacti, Munin, and Nagios plugins so that you can go out and you can monitor Cassandra in any way that you see fit. Again, we talked about the CAP theorem. There are lots of ways to achieve consistency, availability, and partition tolerance in different ways. This is a pretty standard access pattern where we have a single node that we're writing to with writes and reads coming into it. And we're not necessarily talking about a Cassandra node, just something that holds our data, right? Another common access pattern in what we have out there these days is, we read and write to one node. And then our writes cascade out to the other nodes, and this way we try to increase the availability of the system, such that if this node fails, we'll have some replicas out there. So in this classic case, failure is a special case, and deciding when to fail over can be questionable about whether or not a node is down or up, and when you should fail over. And the other thing is, if you have multiple secondary nodes out there to increase your reliability, you have to decide at some point who the new master is. And then when your old master comes back up, what do you do for that case? And then there's another special case there where you deal with the failure of a slave. So there's some popular variations to this. One is where you write and cascade your writes and read from the cascaded nodes. Another one is where you read and write to master, and then you have asynchronous replication behind, in which you have many of the same problems. So if you don't have a single point of failure, or to avoid a single point of failure, basically what Cassandra does is it has a peer-to-peer system where writes come into the system, and they could come into the system from any node. And between those nodes, there's synchronous and asynchronous communication between the nodes, in which they try to remain consistent with one another. In this case, failure is not a special case. If we remove a node from the system, all the remaining nodes in the system continue to operate as they normally would, which is quite nice. So the other thing that falls out of this is that in Cassandra, there's no concept of a clean shutdown. Kill-9 is an okay thing to do. I hope you'll never read on a mailing list, I kill-9 my Cassandra process and it's not coming back up because it's designed so that you can kill-9 and that's okay. There are some facilities in Cassandra, there are some tools that you can use called drain and flush, and most of those are to make sure that the commit log has been fully played, or the mem tables that are associated with commit logs have been flushed out to disk. And so the commit logs are marked clean, they don't have to be replayed when you start a node back up, and then it comes back much faster at that point. Data modeling in Cassandra, we talked about Bigtable a little bit, and Cassandra in many ways uses the Bigtable model for its data modeling. Dynamo is a more similar system to Cassandra in terms of the way it does replication and those types of things. Yet, for Cassandra, data modeling is still very much like Bigtable with a couple of caveats. The motivation for us to use a system like Bigtable is summed up by this quote from Twitter. And maybe some of you have had similar experiences to this, hopefully not to this scale. But basically they said 15 months ago, it took us 2 weeks to perform an alter table on the statuses table, right? And if any of you guys are DBAs or even managers of DBAs and they tell you it's going to take 2 weeks to modify the schema, they'll probably have some choice words to share with you after you tell them that. Or you'll be very scared because you just received that message from someone. And you have to worry about working in some sort of degraded state during that 2 weeks time where that executes on your system. So in order to solve this type of problem, Bigtable basically has, or Bigtable or Cassandra, basically has 2 ways to look at data. They're not logically different within Cassandra. Well, they're not physically different in their implementation or anything. There are no special cases in Cassandra for these two different types of table implementations. But basically, you have two things. You have static column families, which store object data, like person data, where you're storing birth date, you're storing information about a person that's basically the same throughout. Then you have dynamic, which look more like pre-calculated queries that answer a question. So each row in this case would answer a question. This is an example of a static column family. Looks a lot like any table that you might build in a relational database. However, as we added people to the system, at some point we decided Jonathan, he was worthy of a site name right here. And because he was worthy of a site name, we didn't have to do anything special in the system. We just added a site name. If we come back later and we ask for a site name from Nate or Brandon or Tyler, we don't have to do anything special. It'll just tell us that piece of data doesn't exist, which is also an important consideration for Cassandra because although Cassandra is a key value store, it does have columns, and unlike a lot of big table implementations, we actually support a slicing operation on Cassandra, so I can get out just the piece that I want. I don't have to get the whole row at a time. This is important because a lot of people like to make really wide rows in Cassandra and in other big table implementations. The other thing to keep in mind here is that each row is sorted by its column name, right? So column names, we talked a bit in the previous talk about NoSQL being schemaless. Well, in Cassandra, that's not the case. Cassandra has a schema. Your column families have a schema, and they've got metadata associated with it. Now, the metadata doesn't limit it to, say, the column names and things like that, but one of the pieces of metadata in Cassandra is, in fact, the name of the column. And the name and the type of the name of the column can determine for you how that column is sorted. So I could use timestamps for my column name, and then I could get a sorted set of timestamps out of there. I could use time UUID. So if I've got something that's got a higher resolution, some activity or event that's happening at a higher resolution than microseconds or whatever your clock's set to, you can use a time UUID, which would give you a point in time and space where your value was unique, and also sorted by that time component. You could use just a regular version 4 UUID and tell it that this UUID is just a lexical UUID. So then it would sort the bytes lexically in here. So here, here we're using a UTF-8 type, which is just fine. If we want to sort things by the name of the column, or we want to sort things by, say, followers right here. So this is a dynamic column family. Each one of these answers a question. Here we want to know who ZZ Nate is following, who Brandon's following, who Tyler's following, and who Jonathan is following, right? So we've got Brandon, Jonathan's following all these people. Brandon's not following anyone. There was probably something there before, but they might have deleted it. And then Tyler, he's following one guy, and on and on. Each one of these rows answers a question, and that's the key concept for a dynamic column family in Cassandra. Also in Cassandra, when you insert a new value into Cassandra, or you update a new value in Cassandra, it's no different than if you were inserting that data anew, as far as the write path. It will just come in, and it will create a new value for that, and that new value will have a higher timestamp value than the existing value. So when we come in and we read, we'll go through and we'll take all the versions of a particular row, we'll merge them together, and then we'll give you the result of that merging. And you'll see the most recent piece of data. Columns are indexed, so if your column gets really, really wide, because we are using this order type for the column name, we can give you very efficient indexing. We can give you login searches into the data. Because we can give you slices, you can say, I want to start here and end here. There's also a special case there where you can start at the end and search backwards to give you, if you're sorting things in, say, a time series or something like that, you can say, give me the last 10 minutes of data, and that's a pretty easy query to make in Cassandra. So